Universality from holographic high curvature gravity. So Pablo, welcome. Go on.
Thank you, Guille, and thank you for the invitation to speak here. Well, here, here at my bedroom, but yeah, you know what I mean. This conference. Yeah. So okay. So I'm going to start with a general message of what I'm going to try to convey to you today, and this is the idea that you can sometimes extract universal information or information which is valid, results which are valid for general CFTs using higher curvature gravities. So I'm going to start with this like preliminary slide, which what I want to say is basically how this works. So in the holographic context, I will tell you that these higher curvature gravities define toy models of conformal field theories, which are inequivalent from the ones which Einstein gravity defines. And the nice thing about this is that very often you can perform explicit calculations in these models using the tools of geometric tools of general relativity or its extensions. And this allows you to do calculations for conformal field theories, which are much simpler than the ones that you need to do if you try to tackle the problems using field theoretical methods. And sometimes, not always, but sometimes you can use this to learn universal properties which are valid for general CFTs, holographic or not. Okay, so this is the outline of the talk. There will be 5 parts. First, there will be like a general section or part which is going to be about some aspects of higher curvature gravities in this holographic context, and a little bit about what is the idea behind this this approach. And then I will give you 4 examples of how this has been applied in the literature to the discovery of monotonicity theorems, to the KSS bound, to the identification of entanglement entropy universal terms, and finally to how the partition functions on certain classes of spheres which are slightly deformed depend on parameters of the CFT. So let me start with some general things. Well, first of all, as you all know probably, the ADS-CFT correspondence is a physical equivalence between pairs of theories, or perhaps in some cases between a theory and an ensemble of theories, whatever that may be, what that may mean, which are very different in principle. On the one hand, we have gravity theories, quantum gravity theories, string theories usually, or always in principle. And on the other hand, certain classes of conformal field theories in which there's no gravity, which live in one spatial dimension less. So we have, in particular, the quantum gravity theories live in asymptotically ADS spaces in D+1 dimensions. And these are completely equivalent in principle to conformal field theories, which live in D dimensions. So this is supposed to be valid at all possible regimes, but in particular in the regime.
Sorry, Pablo, I think Andres has a question. Andres, maybe you can unmute yourself. Sorry to interrupt you. Andres Anabalón. No, you have your...
Okay, now. Hi, Pablo. I have a question because there is this result by Edelstein, Maldacena, and other people, Tamaño.
Yeah, I'm going to get there. I'm going to talk about that at some point. So
okay.
Ask me at the end if I didn't satisfy your concern.
Yeah. Okay. Then I let you go on.
Good. Okay. So in the regime in which the CFT is strongly coupled and the number of components of the fields are is sufficiently large, then you can see that the description in the gravity side is just the classical Einstein gravity or supergravity in general. So you can describe the physics by a classical action in which you have your cosmological constant, which I already chose to be negative, and your Einstein-Hilbert piece plus matter, which comes from whatever supergravity theory you have. So we can use the tools of classical gravity in this regime to learn quantum things. There are corrections to this, of course, because we are in a very particular regime, and in particular you have stringy and quantum corrections, which come from the fact that the theory is not really a field theory, but it's a string theory, and the fact that this is a classical thing and the theory is quantum. From the CFT point of view, this can be understood as finite N and finite coupling corrections. And typically, in particular, the former come in the form of higher curvature corrections. And an example is the one that I have here, is for a 10-dimensional type 2B string theory. You have the effective action, which is just n equals 2 supergravity in 10 dimensions at leading order. And there is a correction, and the leading correction is in alpha prime to the cube. And this includes higher curvature terms. In particular, a nice way to see this is how this reduces to 5 dimensions. In particular, the gravity sector can be seen to be completely equivalent to this effective action in 5 dimensions, where what you have is the instant gravity action, plus cosmological constant, of course. And you have a correction that involves 4 Weyl tensors contracted with each other, and well, a couple of different contractions of the Weyl tensor. So you see that the instant Hilbert piece gets corrected by these kinds of terms. Well, this is one of the perspectives, perhaps the most rigorous in a sense, but there are others that I'm going to show you. I'm going to tell you about a different one in particular. The one that I show you is about these top-down constructions in which you start from string theory or supergravity, and you get corrections to the effective actions by, for example, the consistency conditions that come, for instance, by imposing that the wall sheet beta functions vanish, and then you get corrections to the leading order actions, right? So there's another approach, which is more like a bottom-up thing. And there what you do is you consider order by order all the possible operators that you may have, and you work with that. And a different possibility is to try to care less about where the theories are coming from, or perhaps they don't need to come from anywhere. And what you do is to consider particular theories which have special properties, for instance, that they allow for simple calculations, analytic calculations, or they improve certain aspects of instant gravity, and they allow you to prove other things. And in the context of ADS-CFT, we will see that they can be used sometimes to learn things which are general. Okay, so I'm going to be talking about higher curvature gravities as I anticipated, but what kind of higher curvature gravities, because there are many kinds. Well, I will be talking about metric theories, and this means that the Lagrangian is always constructed exclusively from contractions of the metric, the Riemann tensor, and perhaps covariant derivatives of the Riemann tensor, although here I basically will talk about theories which involve only the metric and the Riemann tensor. Well, of course, if this was a supergravity action, there would be also things that involve coupling the other things to the metric. For instance, terms like this, which could appear if you have a one form, for instance. But here, I will be talking basically about purely gravitational theories, and in particular, extensions of Einstein-Hilbert, which means that you have some Einstein-Hilbert action, and then you have corrections. In principle, I put only an index here, n. This means quadratic, cubic, quartic, etc. And in principle, there could be, and there are several densities at each order. And these are the kind of actions that I will be considering during the talk, where these densities will be constructed from contractions of the metric and the Riemann tensor. Okay, so there are many kinds of higher curvature gravities that one can consider. In particular, order by order, you can see that at quadratic order there are 3 possibilities, at cubic order there are 8, at quartic order there are 26, at fifth I think it's like something like 50 something, so they grow considerably. The simplest case is quadratic theories, in which you have 3 possible terms, which are these. These were studied, for instance, by Stelle. He showed that this theory is normalizable in 4 dimensions, but you pay the price of losing unitarity. So this is an example of a theory that you may use to perhaps try to improve, as a toy model of quantum gravity, try to improve some aspects of Einstein gravity and see where you can get. F of R gravity is perhaps the simplest generalization, where what you do is just consider, besides the Einstein-Hilbert, or perhaps even without it, some function of the Ricci scalar. These are equivalent to scalar tensor theories and appear all the time in cosmology. There are thousands of papers with this. In particular, the Starobinsky model is an example of this. Another important class relevant in dimensions higher than or equal to 5 are Lovelock gravities, where Lovelock gravities contain Einstein gravity as an example. And these are the most general theories which have second order equations of motion. In particular, well, what characterizes them is the fact that in even dimensions they coincide with the Euler densities of each of manifolds of that number of dimensions. For instance, the Ricci scalar is topological in 2. The next is the Gauss-Bonnet term, which is a combination of these 3, and it's topological in 4. Then the cubic is topological in 6, and so on. There's another criterion that I'm going to tell you, which is a bit different, but it will allow me to introduce some theories that we will use later, that I will mention later. So as I said before, if you ask for your theory to have second-order equations of motion for all possible backgrounds, then you get that the only possibility is log gravities. In particular, in 4 dimensions, you have Einstein gravity and nothing else. You can relax this a bit and consider that the trace of the equations of motion is second order instead, and then you get a particular class of what is called quasi-topological gravities now. You can relax this even a bit more, and then you ask only for second order equations on maximally symmetric backgrounds, only perturbations around the vacuum propagate with second order equations. And then an extra condition, which may seem a bit weird here, but I'm not going to spend a lot of time speaking about the properties of this theory because I'm more interested in applications, but the extra condition is that black holes, which are spherically symmetric and static in this theory, are characterized by a single function, and the function satisfies an algebraic equation, and that's actually something that contains the previous cases, and these are what are called quasi-topological gravities more generally, and if they contain this other case and also log gravities as subcases. All these only exist for dimensions higher than 5 or equal to 5. So what's the best you can get in 4 dimensions? Well, the best you can get is what are called generalized quasi-topological gravities, and these have second-order equations on maximally symmetric backgrounds, and they also satisfy this condition that black holes are characterized by a single metric, which is a second-order differential equation as opposed to only standard quasi-topological gravities for which it is an algebraic equation. So, and all of these are contained in each other. So Lovelock is contained in quasi-topological type 1, which is contained in quasi-topological type 2, which is contained in the generalized quasi-topological class. Okay, so now I get to this idea of getting information about higher-order gravities using holography. So the first point is that, well, you can see that they belong to universality classes. They define CFTs which are inequivalent for Einstein gravity. You can see this quickly, for instance, by computing in the case of 4 dimensions, the trace anomaly coefficients A and C. These coincide for Einstein gravity, and they coincide, for instance, also for supersymmetric CFTs, but they do not coincide in general if you include higher curvature terms. As I said before, sometimes, and I will give you examples, you can compute things explicitly, things which are not easy to compute using CFT techniques. And the idea is that if there is some property which is generally valid for CFTs, then if these theories respect the general principles of conformal field theories, and they do often, although, and there are some things I have to say about that, and I will say them later, there may be some problems in some cases. But if they do, then they will also satisfy these properties. And if you see that they are satisfied by a family of theories like this, you can say, oh, maybe they hold in general, and then you can test this and you can learn new things. And I will show you examples of this. So something which is relevant for this is the fact that for Einstein gravity, there is a single dimensionless parameter, and that this is the quotient between the action scale, or the ADS radius, if you want, and the Planck length. That's the only parameter that appears. So any charge that you compute will be proportional to this thing to the power, whatever, d-1 typically. So if you introduce higher order terms, what happens is that you break this degeneracy. So different charges will have different dependencies on the new parameters that you have in your theory. In particular, for Gauss-Bonnet, for example, you get an extra parameter, this coefficient, this coupling here. So for instance, if you compute the trace anomaly coefficient for Einstein gravity, you no longer get that A and C are equal to each other, but you get you can distinguish between them. And for lambda Gauss-Bonnet different from 0, these two things are different from each other. Okay, so let me start now with the examples of this, and the first one is going to be about monotonicity theorems. And for that, let me drink some water.
Pablo, may I ask you a question? In that theory that Stelle studied long ago, you mentioned he found non-unitarity, right? In all these other theories that have higher equations of motion, namely third order, fourth order, etc. Is there any problem of unitarity in those cases?
Yeah, in general, for instance, in the case of quadratic gravity, already at the perturbative order, you have a ghost mode that propagates, so that's problematic. Even if you just want to quantize fluctuations around the vacuum, for instance.
Exactly. So in these theories you mentioned, I know log-log, they have second order equations, but the other, the topological gravities, do they have second order, the quasi-topological gravities?
No, as I say, they have, the nonlinear equations are fourth order in general. That's what log-log theorem tells you. So it cannot be. I mean, in 4 dimensions, the only possibility if you ask for second order equations is Einstein gravity.
I see.
So and that may lead to other problems, and I will mention one of those problems later when talking about the KSS bound. And then the question is, how much information can you get from there, even though there may be problems with them? And then, of course, you have to see that whether there are problems or not, depending for what things like causality, unitarity, these kinds of things, or evolution in time, or things like that. I will show you that in some cases, even though these theories, many of these theories have fourth order equations, you can use them to learn things, and they are quantitatively correct. I mean, quantitatively exact. It's not even that you can doubt whether they are giving you something correct or not, because they give you something that you compute from a different side and you get exactly the same number. So,
okay.
A question related to that. So in a fourth order theory, such as quasi-topological, even though you can restrict yourself to some sectors in which they become second order by chance, but let's say in general, how do you define the variational principle?
The variational principle.
What do you get fixed? It cannot be as in general relativity, so you have to make an additional prescription. Which is the one you choose?
Yeah, no, but that's okay, but that's for a particular problem. It depends on what kinds of questions you want to ask your theory. I mean, at this point, I'm not interested in, or the question is whether you can determine what the equations of motion are, or, for instance, or, so, I mean, you can do Einstein gravity. You cannot hear me? Can you hear me?
Yeah.
You were not hearing me before?
No, I think the problem is that Gaston cannot unmute. I don't know why. But let me find him, but I don't know why.
I don't know why it's you, Gaston, because I think, I don't know if
Gaston.
Now I can, so I don't know. So, but you wrote an action, right? If you write an action, you tell me that this is a theory, you have to tell me which is your variational principle. It's not a different problem.
No, that's fine. I mean, for instance, I mean, you can see what the generalization of the Gibbons-Hawking term is, depending on what you want to fix at the boundary, for instance.
Exactly, that's my question. What do you fix at the boundary?
Yeah, no, it depends. I mean, it depends on what kind of calculations, what you want to do for different things. I mean, for example, if you want to compute an on-shell action, for instance, you can see that there is a way to find a smart choice for the generalization of the Gibbons-Hawking term.
But in holography, in the context you are talking about, I'm interested in holography. In holography, what do you fix at the boundary?
No, but
why is it funny?
Okay, I don't understand. How can I say this? So, I mean, if you don't include the Gibbons-Hawking term, for instance, in Einstein gravity, you get the piece with the equations of motion times the variation of the metric, and then you get some other piece which involves, I don't know, the variation of the Riemann or something like that. And then what you do, you introduce the Gibbons-Hawking, and then that allows you to fix only the metric at the boundary, for instance, or something like that. For these theories, you can see that generally you need to fix things like, for instance, the Ricci scalar at the boundary or things like that. You need to fix not only the metric, but also derivatives of the metric and things like that. But what the equations of motion of the theory are is something which is well defined. Then whether the variational principle is well posed or not is something that may be important, for instance, for computing on-shell actions or for computing Hamiltonian evolution or things like that. And then well, okay, for computing on shell actions, I could show you examples, and I will actually tell you an example of how of something that we have done in this context, and then you need to see how you do it. I mean, it's not trivial, it's not uniquely determined, it's not easy, but you can do it in a smart way such that you get sensible answers. But as I say, it depends on the problem. I mean, saying, for instance, that the equations of motion of a higher order gravity theory are not well determined because you are not adding a boundary term. I don't agree with that. And it's like, sorry, he cannot. I don't know if he was actually hearing me.
I don't know what's the problem, Charles. Why Gaston doesn't?
I don't know either.
Now I can. So what? You don't agree with something I didn't say. So the question.
Sorry. Okay.
To make holography, you need to impose boundary condition. You tell me that there are more than way of doing. For instance, you mentioned fixing the rich scalar and so on and so forth. Of course, you need an additional boundary condition for a second order combination of the metric. Let's say the scalar curvature. But then in holography, we know that this triggers new fields in the boundary, right? You put a new. So which are these fields? I mean, the stress tensor is for the metric.
For instance, you get that the stress tensor is dual not only to the normalizable mode of metric, but extra stuff. But you don't need to care. I mean, depends on the kinds of questions you want to make. I mean, the question is, can you answer precise questions in the context of?
Well, I give you a precise question. In a metric, in a gravity theory, you always have a graviton. Let's say with local degrees of freedom, dimension bigger than 3. So because in the dual theory, you always have a stress tensor. But if you have additional theory fields here, you have additional fields in the CFT.
Yes.
It restricts the kind of CFTs you can describe, obviously, because you have additional rank 2 tensors.
Yes.
So then, for instance, the question is very concrete: is what is the family, or which is the subsector family you can hope to be dual to these theories? Because it cannot be whatever; it's more restrictive. That's all.
Well, but what I'm saying is that there is a certain, or there are certain sectors of the theory of the holographic CFTs defined by these theories that you can access without caring about, for instance, what are the extra modes which are dual to the metric. For instance, how the stress tensor 2-point function normalizes. For instance, when you introduce one of these corrections, you can see that there's going to be extra modes. But the normalization of CT, for instance, is well defined. Is something clear. Is related to how you normalize the Newton constant, for instance, in the bulk. And so there are questions that you can ask. Some models which are trickier. You get where you can. Okay, so maybe I should continue. Okay, so the first thing I want to tell you is about monotonicity theorems. One possible approach to saying what quantum field theory is about is which is modern, more or less modern, is saying that it's about how quantum field theories change, or how the theory changes as you change the scale of your theory. And in particular, if you move from the UV, if you move from a theory which is at high energies, where you have a very fine grained description, and you move to lower energies, what you have to do is to integrate out higher energy degrees of freedom, and then you are losing information. Just like when you do like real space normalization group, you start with the spins, and then you like average over the spins, you get a smaller spin every time, and so on, right? So, this is what RG flows are about. It's about coarse graining microscopic degrees of freedom, which are heavier than the energy scale at which you are probing physics. No? This results in a trajectory of theories, and in one particular case in which we are considering quantum field theories that interpolate between fixed points, what you get is some conformal field theory at high energies and some other conformal field theory, which is both of them are fixed points of the group of the flow, and you may have in principle different flows, but you have like a trajectory of theories that move from high energies to low energies. And the idea is that, the number of degrees of freedom that you have at high energies should be higher than the number of degrees of freedom that you have at lower energies, just because you are losing information by doing the process of coarse graining. So finding functions which quantify the effective number of degrees of freedom is an important problem in quantum field theory. These functions are what are called C functions usually, and this lambda is like what a parametrization of trajectories here. And it's not an easy problem in general, even though intuitively it's clear what should happen. No? Well, in particular, you know that this function should be such that at the UV fixed point, the number has to be higher than that the IR fixed point, obviously, because you have less degrees of freedom when you are in the IR theorem. So, well, there are C theorems in many dimensions now, although many of the results are pretty recent, in fact. The oldest one is the Samolotchikov's proof of the C theorem, which is from '86, I think. And in that case, you can see that at the fixed point, the C function coincides with the Virasoro central charges of the UV and IR CFTs. And there is another proof using entanglement entropy by Cassini and Huerta. In 3 dimensions, the analogous thing would be what is called the F theorem. And at the fixed points, the C function coincides with 2 things which are equivalent to each other. They are the same, which are the free energy of the CFT put on an S3, or the entanglement entropy universal term across an S1, or the entanglement entropy of a disk in flat space. And the only version of this which has been proven is using entanglement entropy, and this is due to Cassini and Huerta again. And in 4 dimensions, what we have is what is called the A theorem. And again, at the fixed points, the C function coincides with the entanglement entropy universal coefficient across, in this case, an sphere instead of an S1, an S2 instead of an S1, which in this case is the same as the trace anomaly coefficient A. This was proven first by Komarkowski and Schwimmer, and then again by Cassini, Test, and Torba using entanglement entropy methods. So you can see that in all cases, there are versions of the theorem which make crucial use of entanglement entropy, but there are also alternative versions which do not in the cases of 4 and 2 dimensions. In the D equals 3 case, there's only the entanglement entropy rule. Good, okay, so 10 years ago, I told you the situation now, but the only proof that was available was Samolotchikov's C theorem. And there was a very important couple of works. There were a couple of very important works by Myers and Signe in which they use holographic higher curvature gravities to give very important insights on what the C function should be in 3 and 4 dimensions, which turned out to be right. So in the holographic context, you can think of these RG flows, or the way that RG flows are engineered is using this idea that the radial coordinate, the holographic coordinate, is like changing the energy scale of the theory, which is actually quite precise, in fact. So you can create an holographic RG flow by considering a metric that interpolates between 2 vacua, which are 2 ADSs in this case. So you have a profile, a metric like this, which has some function here that goes between ADS1 and ADS2, which would be like the theory at the UV and the theory at the IR. As I say, the flow is parameterized by this radial coordinate R here. And well, the idea is not very complicated. The idea is that you can define a function that depends on this metric function here, such that if using Einstein's equations or whatever gravitational equations you have, if the null energy condition for the matter is satisfied, then the first derivative of this thing is positive for all R. Or in other words, this function is monotonously decreasing along the radial coordinate along the RG flow. In other words, AR is a C function, which is what you were looking for. This is more or less the idea. So what they did this in the context of higher curvature gravities, basically for Gauss-Bonnet and quasi-topological gravity. And one first thing that you can see using these theories, which you cannot see using Einstein gravity, is the fact that you can distinguish between A and C. In particular, they were able to show that there is a hope that the A theorem may have something to do with the A charge, but cannot have something to do with the C charge, because you can see that the functions coincide with the A charge at the fixed points, but there's no condition on the derivative of an analogous function that you could define that goes between the C's instead of the A's. The second thing that they observe is that they using these ideas is that there was a candidate for a C function in 3 dimensions that people have not considered before, and that is the entanglement entropy universal term across an S1 in 3 dimensions. So the thing that I mentioned before, that also turned out to be the right insight. And finally, the fact that they managed to prove these monotonicity theorems for families, for several CFTs to higher curvature gravities, both in even and odd dimensions, suggested that in the cases of 3 and 4 dimensions, which were not proven at the time in general, could be on the right track, and what were the quantities that should be involved in the thing. And in fact, that's what happened later, because in 3 dimensions, the entanglement entropy candidate suggested by this analysis was precisely the one that turned out to be involved in the proof of the F theorem in 3 dimensions by Cassini and Huerta. And similarly, in 4 dimensions, the result was also correct, because the A theorem involves the charge A, but does not involve the charge C. And this was proven later in general by Komarkowski and Schwimmer, and again using entanglement entropy by Cassini, Teste, and Toro. So this is my first example, and now let's move to the second, where, yeah.
Can I ask you one short, and if it's long, the answer, push me to the discussion session.
Okay.
How in these proofs, how do they relate the entanglement entropy with the T mu nu correlator? That's what defines A and C, right? Field theoretically, right? So how the entanglement entropy is linked to that?
Right. Okay. You can sort of see it from thinking that entanglement entropy comes from Renyi entropy, and Renyi entropy comes from a partition function in a replicated geometry, and you need to take like a derivative of that, and it's like a derivative of a partition function, so it's like
it's a correlator in the end.
Sort of, yeah, sort of T mu nu appears there.
Okay. If you are doing derivatives respect to the background metric, I agree.
Yeah, exactly. This you can see, for instance, in Solodukin's paper. It's the argument is something like that. It's actually pretty short, but it's basically something like that.
All right. Thank you.
Okay, about the KSS bound, and this is going to be different because here I'm going to use higher curvature gravities for something else, which is to try, and this is where it's not clear whether or not is the case, to try to disprove universal bound. So this is going to be the only case in which we use them to find something non-universal or disprove something that was claimed to be universal as opposed to the other. Okay, so one of the dreams of ADS-CFT practitioners is to produce predictions that may be tested by actual experiments and get a Nobel Prize, perhaps. And the paradigmatic case of this is perhaps the KSS bound for the shear viscosity over entropy density ratio for a fluid or a liquid. This is perhaps a notion which is not that familiar. It's not very familiar to me either, to be honest, but okay. You can define it. It has to do with the frictions, internal frictions within a fluid, and you can say that this thing is defined for a liquid or a plasma which is slightly out of equilibrium in terms of the subleading correction to the stress tensor in the rest frame of the fluid. So, at leading order, you have the pressure, and at first order in derivatives of the velocity, you get something which is controlled by this shear viscosity. It is a sort of a measure of internal frictions within the fluid. Anyway, what Kovtun, Son, and Starinets observe is that, quite remarkably, the quotient between this shear viscosity and the entropy density of any conformal plasma holographically dual, that's my nephew, dual to a Schwarzschild ADS black hole, or in fact, any black hole solution of Einstein gravity coupled to matter in any number of dimensions, satisfies the relation that the eta over S is 1 over 4 pi in natural units. So, well, it is remarkable that this doesn't depend on the dimension, or it doesn't depend on whether you put matter or not. And it is also remarkable the fact that for all known fluids in nature, this thing is actually a lower bound. So for all known fluids, eta over S is larger than 1 over 4 pi. And this includes, in particular, a case in which this number is supposed to be very small, which is the case of the quark gluon plasma, which is currently being explored at the ALICE experiment at LHC. And the predictions for this are something like 2.5 times 1 over 4 pi, so it's pretty close to this possible bound. So the conjecture was that this is a universally valid bound, and this is a plot from their paper in which you see examples of helium, nitrogen, and water at some pressures and for several temperatures, and you see that the viscosity bound is always satisfied for them. So there was a lot of work trying to explore the validity of this bound beyond instant gravity. And for this, people used higher curvature gravities, which are a natural thing to use here. And for higher curvature gravities, the first approach was to use certain physical requirements to restrict the allowed values of the coupling. So in particular, you can ask for the spectrum of excitations of the plasma not to propagate things faster than light, or that the energy of the plasma doesn't become negative, which may happen also in these kinds of theories. And taking into account some restrictions like that, then it was found that the bound could be violated, assuming these restrictions, in dimensions higher than 4. In particular, it was shown that for Gauss-Bonnet and for quasi-topological gravity, you get something close to 0.4, the original bound. You can lower it a little bit to less than half of what was supposed to be the case for instant gravity. And in fact, in this work by Edelstein, Camaño, and Paulus, they showed that for sufficiently high dimensions in Lovelock theories, you can actually get arbitrarily close to 0, provided you satisfy the conditions that they assume in that paper for the couplings. So these results, in principle, suggest that this bound doesn't necessarily have to be universal or satisfied by all fluids in nature. So there seem to be 3 possibilities. It may be that we are not considering all possible constraining conditions on the couplings that one may think of. And in fact, the bound is true. And these things by Gauss-Bonnet and quasi-topological gravity are just because we are allowing couplings of the values of the couplings to be larger than they should, for instance. It may be that there is some lower bound, but it's lower than the KSS1. That's another possibility. Or perhaps there's no bound at all. No? So something that changed the whole thing considerably, I think, well, that's my impression from, I mean, looking at this thing from the perspective of nowadays, let's say, where the doubts raised on the use of non-perturbative higher curvature gravities here. And the point is that they show, Edelstein, Camaño, Maldacena, and Sibodedov, they show that higher derivative gravities, if you consider them with non-perturbative couplings, in other words, not as perturbative corrections to instant gravity, but with finite values of the couplings, then, at least in the case of Gauss-Bonnet, but probably in general, or for most of them, or whatever, you get problems with causality unless you include in the spectrum additional modes. So it is, in general, not clear under what conditions these extra modes are going to play a role. And in fact, for many of the things, and the ones in particular that I'm going to show you later, that's the case, such possible degrees of freedom, in which cases they play a role or they don't play a role. But of course, in order to make a statement about the possible validity of a bound in which we are actually using other constraints related to physical requirements to constrain the allowed values of the couplings, here, and we are getting a bound that is telling us that the couplings have to be 0, basically, then naturally this led to people to think that, okay, then we are not sure whether we can trust or not the results that we are getting for quasi-topological and Gauss-Bonnet, for instance. I think that's my impression from the reviews and what people say now is that the current belief seems to be that there is some non-trivial bound, which is probably lower than the KSS1 and in general dimensions, but of course this result by Edelstein, Camaño, Maldacena, and Sibodedov tells you that you have to be careful when extracting general conclusions about using higher curvature gravities, not as non-perturbative things by themselves. That doesn't mean you cannot use them at all, and I will show you examples in which you can. But I think this is the question that Andres, this is the work that Andres was referring to at the beginning. Good. So now I'm going to show you examples in which you can use these theories to get quantitatively exact predictions that extend beyond holography, and I will tell you 2 cases, and I'm doing bad with time. Okay, but let's try. So in the case of the first case that I'm going to tell you is about entanglement entropy. So entanglement entropy is something that is well, not well defined to be completely correct in quantum field theory, but it contains quantities. It contains terms that are well defined in the continuum. These are what are called universal terms or regulator independent terms. And understanding what kind of information they encode about the theory is an important problem in physics as well. And one of the issues here is that entanglement entropy calculations in quantum field theory are difficult in most cases, even for free fields, especially for dimensions higher than 3. So in the case of holography, again, we can use these modified theories because we have the Ryuta-Kainage prescription and its generalizations that allow for very simple or quite simple compared to the field theoretical ones, calculations in general dimensions. So I will show you an example of this. So, well, perhaps I shouldn't spend time telling you what the Ryuta-Kainage prescription is. It is about computing entanglement entropy for a CFT, for a region in the boundary. And the idea is that you need to extremize all the surfaces that have the same boundary as the region in the CFT, in the CFT region, let's say, and compute the area of the one that has the minimal area. This is valid for instant gravity or for instant gravity coupled to things, to other fields. For higher curvature gravities, you need to modify this functional and you get something like a wall-like piece, just like for black hole solutions, analogously to the Bekenstein-Hawking one. And then you have also corrections that do not appear for black holes that involve extrinsic curvatures to different powers. The first term is extrinsic curvature to the 2, and then you have other things or the 4, etc. But anyway, you can compute things in a geometric way, which is simpler. And the case that I'm going to tell you is something that we did some years ago, and involves the entanglement entropy of regions in 3 dimensions that have singular that have corners in the regions. So in that case, the entanglement entropy gets an extra term, which is logarithmic. So for if there was no corner at all, this thing wouldn't be here. And there is a function that depends on the opening angle of the corner, right? Well, in the smooth limit, in the limit in which this thing becomes smooth, this disappears. And when it's just slightly away from that limit, what you get is that this is the functional dependence, which is general for all CFTs, and you get some quantity that characterizes that regime that is called sigma. And we would like to know what kind of information does sigma capture about the CFT. And okay, we could compare, but I'm going to tell you what we are going to be comparing it with because I know the answer already. And I will be comparing it with the stress tensor 2-point function charge. So perhaps you remember that the stress tensor 2-point function is completely fixed by conformal symmetry in general dimensions. So this is a tensorial structure which is the same for all possible theories you can consider for which if it's a CFT. And the only theory dependence is through this charge CT, which in 2 dimensions, for instance, coincides with the Virasoro central charge. Good. So we computed this for a higher order theory, and this is the higher order theory we consider. And I'm going to give you already the final expressions. The final expressions are that you get the instant gravity result that takes this form. This is the ADS radius. And you see that there is an overall factor that involves many of these couplings that appear here with some numbers, which are very particular, very concrete numbers, like all numbers. In the case of CT, you can compute this from basically the normalization of the Newton's constant, as I was mentioning before. And if you do that, you get exactly the same answer. You get the same correction to CT. So you get that CT is modified with respect to the instant gravity result by an overall factor that has exactly the same numbers in front of the same higher order coupling, so that the quotient of these 2 things is the same for all higher order gravities, and is the same as for instant gravity, and the result is this pi squared over 24. So this is surprising because in principle, if you compare, and you can compare it with other charges which are not CT, you will see that they differ. This thing will depend on all the couplings that you have here because there will be different numbers appearing here. So at the time, there were the only available results beyond holography were by Cassini and Huerta, and the results were these super huge messy integrals. And luckily, there was also the result for the Fermi and the scalar for CT. So what you can do is try to evaluate these integrals numerically. And if you do that, you say that the result precisely agrees with what you would expect in case you trusted our conjecture to be valid for general theories. And later on, Elbang and Antonis proved actually that these crazy integrals actually give you what our predictions from higher curvature gravities say, namely that for the scalar this is 1/256, and for the Fermi is 1/128. So at the time we conjectured this to be valid for general CFTs based on this, and eventually this was proven by Faulkner, Lake, and Parricard using field theoretical techniques. So this is my first example, and let me tell you the other one, the last one. And here I'm going to be talking about partition functions on curved backgrounds. In particular, I told you before that the free energy of a theory on an S3 is an important thing because it has to do with the F theorem. So one may wonder, how does this change when you deform the sphere a little bit geometrically? You consider something which is not a round sphere, but something close to it. And in particular, a particular class which is particularly nice is one that is defined by this kind of metric. These are also Hopf vibrations over S2, just like the round sphere, but instead of preserving an SO4, they preserve an SU2 cross U1 subgroup of isometries. Well, what is relevant here is that we are deforming the sphere a little bit, and the deformation is parameterized by this parameter epsilon, such that when I put it to 0, I get the round sphere, and when it's different from 0, it's something else. Well, and this is interesting for various reasons that I'm not going to mention, but it's a question that you may ask how the free energy changes when you deform the sphere a little bit. No? So one can show using, from the field theory side, you can prove some things in general, and you can prove actually that the free energy changes like this. You get the result for the round sphere, and then you get a correction that is always controlled by this CT and is quadratic in the deformation parameter, when I'm talking about the deformation parameter being very small, which means that the round sphere is a local maximum and that the leading correction is controlled by CT in a way that is the same for all possible theories. So one may wonder what happens with the cubic piece, and you can say from the field theory side that this thing is going to depend on correlators of the 3-point functions of the stress tensor, 2-point functions of the stress tensor, and also correlators that involve the stress tensor and variations of the stress tensor with the metric. And evaluating this even numerically, it is very complicated and it hasn't been tried at this point. So we decided to look at this using holography, using higher curvature gravities. And well, here we use just ADS-CFT. And the idea is that what has to look for are like the metrics that have the right boundary conditions at the boundary, and they have the smallest on-shell action amongst all possible metrics that share these boundary conditions. In the case of CFTs on squashy spheres, these are what I'll call the Taub, NAT, or Bolt backgrounds. And you can see these are characterized by something called NAT charge, and you can see that it relates to the squashing parameter in a particular way. So in particular, for instant gravity, you can do the calculation and compute the free energy, and you see that interestingly, the result is exactly it's actually a polynomial which is quadratic in epsilon. So our approximation for general CFTs, this thing here, is actually the exact result for instant gravity. There's no cubic piece at all because this is the full answer in fact. So we cannot say anything about the cubic piece using instant gravity, of course. But we tried with a different theory. And what we need to do is first find the Taub solution of the theory. Then we need to evaluate the action on the solution on shell, regularize it properly, and then try to write the result in terms of the dual CFT parameters and see what you get. And well, we did this for Einsteinian cubic gravity, which is the simplest generalized quasi-topological gravity in 4 dimensions. It is Einstein gravity plus something else, which is cubic in the Riemann. And the result, if you do this whole process of finding the solution, evaluating on shell, rewriting, etc., you get that we get the answer that we were finding from the field theoretical side. And then we can say something else about the cubic piece. And the cubic piece turns out, in this case, and for this theory, to be given by something that appears in the stress tensor 3-point function, which is this charge T4, with a very concrete number 630. So at this point, one may wonder, okay, is it possible that this result is in fact general, that it holds for all possible CFTs where of course you need to plug the values of CT and T4 and FS0 for the corresponding CFT. And well, if that's correct, then you can see that a way to prove that is to test that in case you have these two things, for instance, numerically, which was the case that I'm going to tell you in a moment. Then you can just solve this expression for T4, and if this thing is correct for general CFTs, then this function should cross 0 at the value of T4 for any CFT that one may consider. So this is what we did. So in this case, the only available results were for free fields, again, for free scalars and fermions. And here the calculation, of course, has nothing to do with holography. There's nothing holography about this, or not much holographic about this. And you need to compute this free energy, you need to regularize them, and for that you need the eigenvalues of the operators of the Dirac and Laplace operators and so on. It's a bit messy thing, but we had the results, the numerical results for these functions of the free energy as a function of the squashing parameter, so we could plot this function. And if the conjecture was true, then we knew that this T of epsilon should cross 0 at the values of T4 for the scalar and the fermion, which were known from long ago to be +4 and -4. And when you do the plot numerically of this function, you get exactly that match. So what one finds is that indeed this thing, this prediction for the cubic piece also holds for free fields. So it's very likely to be true for general CFTs as well. And in fact, at some point, we managed to prove this also for an infinite family of holographic generalized quasi-topological gravities of all orders. So we are pretty confident that this is actually right in general, but it hasn't been proven using CFT methods yet. And that was it. I leave you with my general message slide that I already read. So I leave you with that. Thank you.
Okay, thank you, Pablo. Very nice talk. Guys, you can applause. Okay, so thank you very much.